Okay, so let's talk about the lab first. So under our first week's laboratories, it looked like people were getting there because I think I've got over half of you have gone in and have found your examples of simple harmonic motion. And so that part is in there. The big thing that I want you guys to do, so you're going to post your videos to the discussion board. We're looking for 3 examples of simple harmonic motion. Then you're going to do a 1-page PDF. So if I go over here, nope, that's should be right there. That's the scoring. There's a 1-page memo that you're going to do for your 3 examples. And one of those examples are let everybody get in here. There we go. Thinking about it. There we go. So for each example, say for example, you have a person pushing in a swing and you use the swing as your simple harmonic motion. You're going to have your amplitude and you can just estimate the amplitude. I'm not forcing you to go out there and actually measure it. But say, for example, you've used a wind turbine as your example of simple harmonic motion. You can go out and go to the internet and get an estimate for how long one of the blades are. And that's going to be your amplitude, is the length of the blade for your wind turbine. So you'll be able to get your amplitude. Then you should be able to time the period, the time for one complete cycle. So if it's something that's going around in a wheel, you should be able to get the time for one complete cycle. And then you can calculate your angular frequency. And that's what I'm looking for. So you're going to write down your position equation for your example. And then explain why whatever you picked is an example of simple harmonic motion. And you're going to do that for each of the 3. And remember, I want references. So you're going to want to include your reference. So this lab shouldn't be terribly difficult. And we should be able to get it all without too much trouble. Questions on the lab? Got a nodding of heads, so that's good. And that, of course, is due by midnight tonight. All right. And then we'll do the simple pendulum next week. But we started with the simple pendulum and had the discussion, and I've got to update that one yet.
Are we doing references pretty much the same as we did the last couple times?
Well, right now I'm not being persnickety about references because one of the things I want to do is I want us to start using IEEE format for references, but I haven't provided you that information yet. So this time I am not caring what kind of format.
Okay, I'll just Google it and Google that particular format just so I get used to it then.
Yeah, but we are going to start using IEEE. And the reason being, guys, that I am going to start doing IEEE is because I talked to several students over the summer and their upper division classes have been using IEEE. So they recommended that, you know, that based on what they were seeing in their upper division classes, knowing the IEEE standard was a good thing to start doing. And it didn't matter if they were in engineering or if they were in computer science but right now, kind of the areas that we're headed to, they're saying IEEE. So for you guys, I think that's where we're going to head is IEEE references. Just to make sure that we've got stuff that's going. So, and Aiden, that should get you what you've got too. Right, but the first time I'm just looking to see that you referenced it. That's all I care about this first time around. Is that you got a reference in there. Okay, so that's the lab. Go back in here. Other things now. I noticed, and IT informed me today, and apparently it's not just happening to us, and I don't know, you may have been experiencing it in your math classes, because the math classes are a Cengage book. Did they talk about something being dorky with Cengage and Blackboard at all? Blank out? No, that's not what I'm talking about. Apparently Blackboard and Cengage are not playing well with each other right now, which is unusual. And because Blackboard and Cengage have played well quite a bit, I have noticed it in two places, and it hasn't been in you guys. It's one of the things I've noticed has been in you guys' class. One of the things I've noticed has not affected you at all. When we link Blackboard to WebAssign so that you have a direct link to your WebAssign link, in my other class, even if the homework assignment was worth 50 points, it was only coming over as 1 point. Now, what was weird about it, it was coming over as 1 point properly ratioed. So if you had 46 out of 50, it was giving you like the 0.7 or the 0.8 or whatever it was out of 1 point, but it was only giving you 1 point, even though the assignment was worth 50 points. So that was the weird thing that I was seeing. And I was only seeing that in one of my classes. I have not seen that in your class. The other thing that it's doing differently, and I want to caution everybody on this, is because it is actually, so when you push in and you submit an answer in WebAssign, right now it's immediately transferring over into the gradebook and Blackboard. So if you've done one problem and you get 1.5 points out of your 50 for the homework problems, it's showing that you right now have only 1.5 points in your gradebook. Well, that's not too bad at the end of the semester. Right now, that's horrible because if you look at your overall weighted grade, it looks abysmal because it's expecting you to have only gotten 1 point out of 50. And that's not right. So nobody pay attention to your overall grade right now because it doesn't look right and it's not quite right. And I noticed that when somebody opened up the next homework assignment, all of a sudden their grade plummeted from a 90 to like a 30. And you're going, uh-oh, something's not right. And I was checking it. So that's what's happening. So the grade book is working correctly in Blackboard, but it's not correct in that homework's not due yet. So it shouldn't be figured in. So it's giving you real time, and we're not sure why. Because historically, what Blackboard would do or WebAssign would do is it would pick up that assignment when it was due or right after it was due, and then it would push all the grades over. So right now, I don't know what's going on.
It's
And
it's working normally. It's always done that in the math classes.
no, it's doing those in my
Update.
physics classes. That's what I'm seeing in my physics class.
Yeah, but as you update it, like you said, it's in real time. But
Yeah,
it's
in
actually
real
done
time.
that way.
Yeah, it's in real time. So something's funky, and I just don't want people to all of a sudden think that they're doing poorly in class because we haven't had that many points yet to be doing poorly in class. And I just don't, and I don't want people freaking out that they're all of a sudden their grade is plummeting and it's not real. So just be aware of that because we've had enough consternation this semester. We don't need to have any more. And I will tell you, IT is working the issue. I sent a whole lot of troubleshooting because I was working with Cengage on this yesterday. Because I've noticed where it's happening, the weird 50 point, 1 point thing is happening in one of our new editions of a textbook. And I'm not seeing it come over for you guys. So just be aware of that. So nobody panic. Nobody panic about a lot of things. Right now, we will get through it and we will work through it. In the assignments and homework, I have released chapter 18 and I have released the quiz for sound and simple harmonic motion, and you will see a practice test. This is the test that I gave for this topic last year. And your test is likely to be very similar to that. So because I know our first 3 weeks have been a little discombobulated and messed up, I wanted to get everybody on the same page, headed in the right direction. And we're going to cover our concepts, but you can also see because you'll see a lot of theory in my videos where I've derived the equations, I've come up with where those things are. And this is the difference between a physicist and an engineer. One of the fundamental differences between physics and engineering is physicists like to go back to absolute basic principles, derive the equations, and use the equations. Engineers, they hope the physicist has derived the equation and they just use the equation. Okay, that's kind of the difference. But the reason the physicists go back to first principles and derive the equations is because we're going to make assumptions. And those assumptions are critical to how the equation gets used. So for example, when we're dealing with traveling waves, which we're about to get into, we talk about tension and we talk about the linear density of the item. So that is why if you have your 6 guitar strings, the different strings are rated for different notes. And you'll have the heavier strings are rated more for the lower notes, and the kind of the nice fish gut strings are rated for the higher notes, but that's based on the mass density or the linear density of the string. Okay, so in my videos, you'll see how we derive that tension sets up for standing waves. And standing waves are related to simple harmonic motion, but they're a standing wave. So our guitar string example, that is a standing wave. You can still relate it back to your position, but it is a standing wave and it's related to both time and position. So that's one of the things that we get in there. So you'll see in all of my videos, you're going to see I've done the lovely gory, horrible gory derivations to get these beautiful simple equations. But you got to know when we can apply them. So remember, the big assumption for simple pendulums is that for simple pendulums and for all pendulums, we're going to make the small angle assumption. And the small angle assumption is that as long as I'm less than 20 degrees, I'm going to be able to use that small angle assumption that the angle and the sine of the angle are approximately equal. Things fall apart if I go greater than 20 degrees. That equation doesn't work. So that's one of the reasons we do all of that. So that's where that piece comes in. But I've given you the practice test. I've given you all those gory details. And we're doing chapter 16, 17, and 18 all kind of together. But you can go in and find all of my horrible gory details. The other thing I want to point out is if you go under here, under learning resources, I think it's right there. This is the link to my YouTube channel. I have put, excuse me, I have put up lots and lots of my general physics and my engineering physics recorded lectures on that YouTube channel. So some of them is, so the difference between what's known as university physics or engineering physics and general physics is how much calculus we use. Pretty much that's it. And physics 2 is where we derive all of that stuff. Right? Physics 2 is where we derive that stuff. So you're going to get all that stuff as we go through. But if we're looking conceptually and we want to deal conceptually, you've got my YouTube channel. So the YouTube channel is there and available. Making sure everything's sharing here. Yes, it is. So also, once you get to my YouTube channel, you can go back and look at all my Physics 1 stuff too. All my Physics 1 stuff is out there. And a number of other fun extra videos that are in there as well. So I just wanted, because I don't think I pointed that out to everybody because of how we started the semester. But I want to make sure you guys have that. There is your link to tutor.com should you guys need it. It's right there. It's in there. So that one's there. This is some citation guides, but again, I'm going to try to find those IEEE items as well. Okay, I closed it before I wanted to. You will also notice that I did start, because some of you have already plugged and chugged and are headed on down the road, which is totally fine. I'm okay with that. I've gone ahead and posted the electrostatics, so the first part of electrostatics work. But you will be getting that test over chapter 16, 17, and 18 will happen over next weekend. But again, you got a practice test to start with. So you got a practice test to start with. All right. I think I have all the all the lectures that I've been doing have been uploaded. I think everything's available. So we can start playing with traveling waves and looking at some energy stuff. Everybody good? Okay. All right. So now I got to do, let's see if I can break things. Let's see if I can break things. I've had all kinds of fun stuff lately. Had IT out, so. Woohoo! And I even have my calculator. Oh, life is good. You can tell it's Friday afternoon. Okay. So, as I mentioned, we start out with simple harmonic motion, and some of you may have heard it before, some of you may not. But the reason I start out with simple harmonic motion at this point in the semester is we are going to, the way Physics 2 works is Physics 1 is mechanics. And Physics 1 follows a logical path. Unfortunately, Physics 2 does not. Physics 2 is a little more esoteric. Now, for some of you, if you struggle, you know, we've got a couple of you that were doing it backwards, which is okay, because there are a lot of people that doing it backwards actually makes it work better for them. For other people, that's not the way it goes, but it's a historical anomaly that we teach physics in this direction. So just remember that. So we will get there. So we get Physics 2. So Physics 2, some people will start with electricity. And then we get magnetism. And then we get the Maxwell's equations. And Maxwell's equations leads us to light, which leads us to optics. But that's a challenge because we don't have in the semester, when we're doing our mechanics, we don't have time to deal with mechanical waves. But waves become extremely important when we get to light. So I like to bring in mechanical waves to start everything because it's going to make some of these things make more sense when we get to Maxwell's equations. But I'm going to warn you that things are going to feel very disjointed when we hit electricity and we hit magnetism, and then we get to Maxwell's equations, and Maxwell's equations starts to tie everything back together again. It's kind of like if you're building a car, you got people working on the engine, and you got people working on the interior, and you got people working on the electronics. And if I'm in the middle of making the sausage or making the car, I don't necessarily see how it all goes together, but all of a sudden at the end, we have a car. That's exactly the way physics 2 works. And I will tell you, I have a love-hate relationship with electricity and magnetism. I have a love-hate relationship. It's really a love-hate relationship because electricity was this esoteric thing for me. I didn't visualize it well. I visualized mechanics very well, didn't visualize, but all of my graduate work, all of my work has tended to be in electricity and magnetism. It's just because I'm a glutton for punishment and I'm trying to figure it out. Okay. But I really love it because I want to get to optics. And optics is where everything, and yes, my laboratory, our laboratory is a graduate student. My senior graduate student in the room and we were actually playing with laser light and we created an optical and or circuit. So we actually have a paper out there to create the first optical and or circuit that happened a long time ago in a land far, far away. And it took an entire room the size of this laboratory or the laboratory at Tonkawa in order to do that. And now they do it in fiber optics all the time. So, but that's one of the fun things that we do. So nobody panic, but we're starting with mechanical waves. So let's start dealing with. So for simple harmonic motion, what we did, we're going to use the spring model because it's nice and easy to look at. Okay, so we've got our spring model, and our spring model is going to allow us to have our amplitude, where this is my amplitude. And this is my amplitude, it's just in the other direction. Okay. And we've been able to say that my position is going to be related to my amplitude cosine omega t plus phi. And my velocity is minus a omega sine omega t plus phi. And my acceleration is minus a omega squared cosine omega t plus phi, where omega is equal to 2 pi times the frequency or 2 pi over the period. Okay. And even though we didn't go through the whole gory detail, what we do find is that for my system, whatever system it is, we can relate that system back to this spring constant. So remember, our 3 models are in our circular motion model and our pendulum model. But I can relate it back to this spring system. And we went back and we looked at force. Remember, force is a weight. And we have a restoring force problem. And we get a spring constant K. And this spring constant is related to the material's properties. Okay, it's related to the material properties, or it could be related into the property of that system, or it can be related into the property of that system. And the reason why we try to go back to the spring analogy is because if I have a chemical structure, think water, right? We all remember that water molecule. Here's my water molecule. That's oxygen. I got a covalent bond with hydrogen, a covalent bond with hydrogen. This bond, in fact, when we do infrared spectroscopy, we count on that bond vibrating like a simple harmonic oscillator that we can define with this spring constant. So we're actually going back to get the physical tie-in to stuff. And what you guys will get as engineers, you're going to get strength and materials. And this is why we have to have these things for strength and materials, because these kinds of constants are going to be that. So this vibration, or this, how this system is going to work, is going to be dependent, because my omega is also going to equal the square root of my spring constant over the mass. So whatever mass I have hanging on this spring is going to impact the frequency. How I make up this spring is going to impact the frequency. And you think of, why is this important? Think of a watch spring. If I'm making a mechanical device that I want to have work in a certain way, I want to be able to construct my system so it's going to behave properly. So a watch spring would be there. So not only, so if I know the period, if I know the period and I can measure this, I can come back and relate it back to certain parts of my equation. Because what we're doing is we're building models of systems. And the physicists love to build models of systems. And in Newtonian mechanics, models can be very, very simple. So this is how we can set up our system. So now let's think about our guitar string. We're going to start playing with our guitar string with the linear density, and we're going to start dealing with a wave that's traveling, because our simple harmonic oscillator is just staying in one place. It's just staying in one place. We're just bobbing up and down. What we're getting ready to do is we're getting ready to take a string, and I'm going to send in a pulse in this string, and it's going to move, and I've got this string attached to a wall, and this pulse is going to actually move down the string. And we've all seen it. If you're in the gym and you want to take that big rope and you send a pulse down, you'll see that that pulse moves. So what's happening?
Honestly, it's just
Well, if I'm the little object here, guess what? This little object here is just moving up and down, right? It's that little point on my string is going to act like a simple harmonic oscillator.
We're doing that. It looks cluttered.
It's just going to go up and down based on where we're.
Not due to like.
Now, if I'm looking at this point, guess what it's doing?
16, even better.
It's just going up and down.
Until after that, just practice that.
And the size of this pulse,
Still,
so this is a pulse.
it still looks like a mess.
The size of that pulse is going to be related to the intensity.
Yep.
Now, if we play the calculus game, right? So let's take the calculus game. Calculus game is, I can look at my string as incremental little changes in mass. And the beauty of calculus is that I can do it infinitesimally. I can get it teeny tiny. And that's the beauty of calculus. Because, so let's kind of remind calculus, just so everybody remembers where the calculus comes in. So the total mass of this system is the sum of all those teeny tiny masses. Or if I do it in terms of the integral, those are my infinitesimally small masses. And if I sum that up, that's going to be the total mass. And if I get my linear density, you know, and we can actually do that. My linear density is my incremental mass per unit length, and I can integrate it over the entire length of the string. So we can go through that gory detail to get us there, but The thing about these things are is that they're all connected. They're all connected. Now, what we haven't talked about, so we're gonna go ahead and define, because again, we've got some folks that were flip-flopping, and we're gonna keep everybody together. And I'm not completely sure exactly how everything went, so we're just gonna redefine everything. Remember, we have conservation of energy. And one of the other conservation things that we have is conservation of mass. Even though it's not gonna be a big deal here, we have conservation of energy, conservation of mass. We're gonna find out that we have conservation of charge when we get there. We also have conservation of momentum. And that can be linear momentum or angular momentum. But I have conservation of momentum. Just to remind folks, momentum is defined as mass times velocity. Momentum is a vector quantity. Energy is a scalar quantity, which is why we like working in energy, right? I don't have to mess with direction. Things are a lot easier to come up with things. I don't have to mess with direction. But I do got to work with momentum. And just to remind everybody that for whatever bizarre reason, which I have yet to find out, and I don't know where it came from, it has been the convention forever that is the letter P. I have no idea why. Okay. So we got conservation of energy, and conservation of energy says, when we're looking at conservation of energy, we get our conservation of energy theorem, is that we have conservative energies and these are like potential energy and kinetic energy. And I like using PE and KE because it helps keep me straight. Our book uses U and K, and I really don't have a clue why we use U. It's just a fundamental, one of the other things, totally there. But, and my non-conservative energies, just to remind everybody, my non-conservative energies are things like friction, because I'm going to lose energy due to friction. I'm going to lose energy due to drag. I'm going to lose energy due to heat dissipation. Those are the things that it's hard to put in a box. We're going to lose those pieces. Hard to put in a box. Now, potential and energy and kinetic energy, those are fairly easy to deal with. We can calculate them. They're pretty easy to deal with, and we can look at it. So let's go back and remind everybody what those potential energies are. So we have two types for a spring system. My spring system, I can store energy. And I can store energy in that spring. So I can compress this, and as long as I'm compressing this and I have a little break on there, my spring's ready to go and I can let it go. And think of a little popper, right? Or a little popper, we'll put it with a little suction cup and we'll push it down on a piece of tape on the table. And finally it's gonna break free from that little piece of suction and it goes pop, because we stored energy in the spring. And our potential energy for a spring, just to remind everybody, is 1/2 kx squared, where this x is our stretch or our compression. It's our delta in the length. So I can either squeeze a spring or I can stretch the spring. I can do one of the two. If I'm in a pinball game, I have pulled my little hammer back and I'm compressing that spring and I'm going to let the pinball shoot off and let it go up. Or if I'm dealing with this system, I can pull the mass down and let it go, and it's gonna bounce back up. My other potential energy is if I put a mass on the table and all of a sudden the table disappears, it's gonna fall. And I have positional potential energy, and that's my potential energy due to gravity. And that's equal to mgh, where h is the height off the floor. Then we have kinetic energy. Okay, we've got our kinetic energy. And just to remind everybody, that's 1/2 the mass times the velocity squared. Now, conservation of energy says the total energy of my system is going to be the sum of all of these energies. So if I'm using the spring one, I got to play with my spring constant. So we're not going to use the spring one. We're going to make it simple so that everybody can remember it. We're going to start with the pendulum. And my pendulum is going to swing through the 0 point and come back up. Okay, my pendulum is going to be there. And this is my height. This part is my amplitude. Okay. Now, just a reminder, when I get to the top of this spot, we know what the velocity is. The velocity at the top, because I'm headed this way, and at the very instant I'm at the top, all of a sudden I refer back to this way, so my velocity is equal to 0. So the total energy at the top is going to equal just the potential energy, because my 1/2 mv squared is equal to 0. Now at the bottom here, my total energy is going to equal my potential energy at the top or at the bottom. And it's going to equal my kinetic energy. But at the bottom, if this is mgh for my system, that's equal to 0. So my total energy at the bottom is only equal to my kinetic energy. And for those of us that have went through mechanics, we know that that is also where the velocity is going to be greatest. So my minimum velocity is up here at 0. The bottom, that's going to be my maximum velocity. And we're going to go through there. Come over to this side, and I'm back to this situation again. So my energy, as I'm going through here, is going to go back and forth, just like my energy would be with the other part. So I'm going to get this back and forth part of it. So I'm going to have this up and down. And you guys have a great, I think it's in this one. If it's not in this one, I'll get you another picture. The damping portion. No, this one doesn't have a good diagram. I'll have to go find you a good diagram. But you're going through that same fluctuations of energy as you're going back and forth. The cool part is when we get the total energy in here, we can play with that too, and we can have it bounce back and forth. So we're going to get energy going up and down as we go through our system as well. So let's go back to our, starting with our traveling wave. So I'm going to get a pulse down our string. Now, when I'm dealing with this part, motion of this part, we're gonna use y just to make it clear. Y is gonna be related to the amplitude cosine omega t plus phi. But this is describing the motion of our little increment piece of the string. The big thing is waves carry energy. Whether that's a mechanical wave or an electromagnetic wave, waves carry energy. I want you to think about that for a second. If I am standing in front of a subwoofer, we can feel it. You can feel it. My grandfather tells a story. My grandfather helped build every dam on the Snake River. My grandfather was an electrical engineer for Idaho Power, ultimately retired as the treasurer of Idaho Power. And he got to help build every dam on the Snake River. And Snake River is kind of interesting because the Snake River, if you go out there and you go look at the Snake River, if anybody's ever been a fan of Evel Knievel, when Evel Knievel jumped over the Snake River, you go out there and you look and it looks very flat until you come up to the edge. And then all of a sudden you look down, it's kind of like looking down the Grand Canyon, and there's a river at the bottom. So it's a great river to block. As a young engineer, he was on a crew that helped build one of the dams. And all the people that were there used to live in the shanty town at the bottom of the bow of the canyon. And they were all there and they had just finished all this nice concrete and they had made it up. And my grandfather had to help dispose of the leftover TNT. If you come to my office in Tonkawa, yes, I do have an Acme dynamite box. And it is from my grandfather's garage. It is a wooden dynamite box. At one point in time in its lifespan, it actually probably about 100 years ago, it carried dynamite in the box. So they had to dispose of the extra dynamite. And they weren't thinking. Being young engineers, we're not thinking of all the potential consequences. Well, they piled up all the extra dynamite and they lit it off. Very large kaboom. It wasn't a dam shattering or an earth shattering kaboom. If you're into Marvin the Martian, it wasn't one of those, but it was enough that they all felt the reflected percussion wave off of the dam as it came back through and blew down the entire shantytown. Luckily, that was the last thing they had to do before they had to get out of there. And so that was okay. And, you know, doing stuff in the 30s is a lot different than doing stuff now. But we know that waves carry energy. We know, and when I think I showed the video, I haven't showed you guys all the video yet, but the video from, yes, you even felt the wave coming off of the Falcon 9 rocket 12 miles away. Waves carry energy. So what's happening as we're sending this
I'm 1%.
is it's transferring energy from one little thing to the next little thing. And it's gonna carry this down. Now, what that's going to do to us is now we're going to have my chapter here, so I'll make sure I write my equation down properly. Because I have slept since then. Is now, instead of just a function of time for this piece, we need to have a function for position and time as it relates to the wave.
Yeah, kind of.
Now, this is a wave that's in a string. This is a mechanical wave. This wave will not go anywhere unless it has this string. And we actually have to have a little bit of tension in order for this to work. If I just take a string and flip it, we all know what's happened. I can get this wave to travel down the edge, but at the other end, it's just gonna go away because we're moving it off. So we're gonna have to have a function of that, and it turns out that we can actually do a function
Yeah, I still got,
of position and time.
I wrote it up early
And
on.
now we can bring
I
this,
didn't
as this
actually-
wave moves through there, we're gonna have that go through there, and our wave
I'll
equation is
just-
gonna be Y max, which is also an amplitude.
Honestly, I haven't, it's actually 2 pages. Because it's disgusting.
And this is gonna
Probably not gonna
be
be great.
A
Great.
X
Yeah.
minus omega.
It's a little bit harsher. Right now.
And in the interest of time, I'm not going through the glory details of deriving that equation.
Swing, the little buoy that went up and down, and then,
And this is for transverse waves.
stick that I threw, I just took video of it. I'm doing it,
That is
analyze.
a transverse wave.
Uh,
This is a transverse wave.
for,
I can see a transverse wave in the stream because I'm gonna get this part that goes up.
I was about to say, that sounds like a pain in the ass.
I hate it.
Same form is gonna happen for something that we call a longitudinal wave.
That's why I wanted something big and like, that you can see.
Can you guys mute your,
Longitudinal waves are gonna go through, so I'm gonna take a pipe here. We're gonna put a speaker at the end of my pipe. And we know how a speaker works, right? The vibration of my speaker goes back and forth. What will happen is what happens in my little molecules of air is I can send a pulse through here. And we get what this is called rarefication. And this is called compression. So essentially what's happening in a longitudinal sense, if I have a gas or a liquid or something hard like my tabletop, my molecules are going to compress and then rarefy, compress, rarefy, compress, rarefy, compress, rarefy. A slinky can show both of these. I can take my slinky out, I can stretch it, and I can send a pulse down. That is a transverse wave. I can compress and extend my slinky, and you can watch this pulse go through a slinky, and this is called a longitudinal wave. I think I've misspelled it. Yeah, let me do it again. It's Friday. So this is a longitudinal wave. Now sound is a longitudinal wave. Sound is a longitudinal wave. Because if you think about it for a second, in order to get a transverse wave, I gotta have a string. I gotta have something connected. It can be water and use surface tension. We've all seen transverse waves in water. Think of my wakes that go out there. You can see that wave roll through. Okay, I can get it. And we actually I had guys that were out when we had the big earthquake a number of years ago. They actually watched the ground ripple. They could actually see the ground ripple. So longitude or transverse waves are going to have something. My sound waves, I still have to have a medium. I still have to have air. I've got to have water, or I've got to have something solid. I still have to have a medium because the classic example that shows you that mechanical waves don't travel is the classic bell jar experiment,
I know.
where you have an alarm clock in here, and it's an old-timey alarm clock, and you have the little bell on the alarm clock, and you have the little knocker going back and forth. And as they evacuate the bell jar to a vacuum,
It's nice until
you'll
it's.
still see that this
Yeah, I was
thing is
about to
moving
say.
back and forth, and so it's ringing, but all of a sudden you can't hear it ring anymore.
What's that?
Because there is no there is no medium for the stuff to move through. So mechanical waves, this is one of the differences.
I'll ask him
Mechanical waves,
about thermodynamics, just out of curiosity.
which are both either transverse or longitudinals, have to have a medium. And I'm gonna stop there because we're now at 1:20. And I know some of you have to go to Therma.
Yeah, that's it.